here we go. So we're going to talk about sketching and getting ready for later in the week. Some of us are discussing worldly issues, so I can only assume that we've actually gotten through the warm-up. I'll go through that in a second, but I thought I'd get us started on the work for today. So the key features of any graph, of any function, what are the key features that we've dealt with in the past? Yes, so we've got the x-intercept, or intercepts. We have the anything else? Any points where there's a change in the direction, so a turning point, a point of inflection, the starting point for our square roots. Does that make sense? So any point where we've got any change in what is going on. Also points of discontinuity. I'll put that as a side note. What does that mean, discontinuity? Yep, so any point where it changes over or the function ends, we usually write in, correct? They're key features on our graph. We don't put every single point because that would be a waste of time. We know how to find our x and our y-intercepts. How do we do that? Substitute. What? We let x equal 0 and we want to find out? And we let y equal 0 and we want to find out? Because that's how intercepts work. Every x-intercept ever has occurred at y equals 0, and every y-intercept ever has occurred at x equals 0. We haven't been able to find our turning points prior to this moment because we haven't had the power. Now we have the power. In the past we've needed in this form, correct? And we know that not every function comes in this form, as our first assignment would have shown us. Calculus allows us to find the turning point for any single function, providing there is one. How do we do that?
Find when tangent equals 0.
Very good. So we find where our tangent equals 0, and this will tell us where our function is? Changing or turning. How does that work? What I want you to do is to draw a polynomial of order 2, 3, 4, 5, 6, 7, 8, 9. You get the idea. Any integer number greater than 1. Draw me a polynomial of that order. I'll give us an example. What type of function should I draw, Jerry? Yep, polynomial. Give me a quadratic, cubic. Cubic, okay. Negative or positive?
Let's go positive.
Positive, cool. Happy with that? That's a cubic, a positive cubic. So, with your function should be something, whatever it is, I don't care what it is, but providing it's one of those polynomial styles. What do you think I'm going to ask you to do now? I've got a ruler in my hand. Progress the tangent as we go around. Now tell me what a line that has a gradient of 0 looks like.
Straight.
Yep. Horizontal. So anytime that happens, we need to alert ourselves and put a dot on our graph. Cool? So anytime your ruler is parallel with your top of your page or the bottom of your page, I want you to put a dot like this. Da, 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 da. We keep going around. This is actually very upsetting that it's got a magnet on the bottom. That looks like a point where it's parallel. I'm going to put a dot there. Da, 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 da. Another point where it's parallel. Da, 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 da. Off we go. So, I'm going to guess if you've done the same thing, you probably saw a very similar thing, correct? That occurs at any turning point. What about, Harry said a word before that I want to draw our attention to. What was the word? Oh, it was 3 words. Point of... What's the difference between a point of inflection and... Because that happens with a cubic, but that's not. There's no points of inflection there, is there? So what's a point of inflection?
Isn't it when like it's mirrored?
Yeah, so a point of inflection when we're doing red, it might look something like this, right? Well, that's not a very good point of inflection. A point of inflection should look something like, there should be a flat moment and then go back up. Cool? If I could draw properly, it'd look better, but I can't. So, think about the gradient. I just want positive or negative, okay? One word, positive or negative. Okay, that was the first example. So in the other examples it went positive, 0, negative, or negative, 0, positive, correct? With a point of inflection, it keeps going the way that it was. So it's positive, 0, positive again. Does that make sense? So if it's a regular turning point, what we'll see is it goes positive to negative or negative to positive. If it's a point of inflection, it'll go positive to positive or negative to negative. Sweet? But that's also a key feature in our graph. So we'd have to identify the coordinate. So let's say I've got my graph here and I want to identify where these functions occur. Hypothetically, if I had a function like this, and I wanted to identify where my, because what have I asked you to do in the one without you realising?
Find the point of inflection.
Find the turning point, not a point of inflection. Oh, it is a point of inflection, I think. Anyway, find a turning point or a stationary point there, correct? Once you've found that, you should have one solution. It looks like one where you get two, but you only get one solution, correct? Or incorrect? Correct. You get one solution. How would I find the coordinate of that? What have I found when I let my f dash x equals 0 and I solve that? What do I get? I get my final answer says x equals. Do I know my y value? How would I find my y value? I would substitute x equals 1 into the original equation. Does that make sense? So what I want you to do is tell me where the stationary point in this graph occurs. So if you finished your one, which you should have, now that you've gone through this, I want you to tell me the location of our stationary point with that example over there. Cool? Let's go.